This is section 17.2 on line integrals. I added another exclamation point to the title. I guess I'm just going to do that for the whole rest of chapter 17 because you've done a lot of work to get this far in calculus and you just need to know that this is awesome. Okay, what's the objective for 17.2? Well, we're going to figure out how to do a different kind of integral called a line integral, which instead of it having a region in the plane that it's focused on, or like a solid in space that it's centered on, or an interval on the x-axis that it's centered on, instead the integral will happen on a curve. And that curve will either be a curve in the plane or a curve in space. So I'm going to highlight, here's how we're going to make a curve in the plane, like with a parameterization, and here's how we'll make a curve in space. And those are the first two kinds of line integrals that we will do. It'll end up being useful to use that kind of line integral to find mass of like a wire that is all curvy. And we'll use a function that's the density function. Then in the second half of 17.2, we do line integrals of vector fields. So I'll turn that on here. The other kind of object we're going to do the integral of. This will be, well, you'll see when we get there, but when you have the idea of a vector field in your head, you should imagine like a force field, like that every point in space has a different gravity arrow pointing, or like wind, that every point in space has a different wind velocity and direction, wind speed and direction. And so every point gives you a vector, and that's a vector field. So let's figure out how to do all this stuff. First, I want to remember like what was going on with the different kinds of bounds in different kinds of integrals. So the very first kind of integral that you learned how to do was an integral from a to b of a function. Well, what was that? Well, the a to b, the thing that's in the bounds of the integral, was like where it's all happening. What you did is you had some function up here, and you took the interval from a to b and sliced it up into really tiny pieces, which are this dx. And then you multiplied f of x times dx, and that gave you the area of this little tiny rectangle, like length times width. And you add all those together, that's the integral sign. But the point is that the thing you chopped up, the like base of the integral that everything was happening on, was the interval from a to b. So this is over, that's the preposition we use, over the interval a to b. And the end result of this integral was that it gave you the area under the function over the interval a to b. Now, in the last chapter, you figured out how to do double and triple integrals, and the bounds referred to the region that the integral was happening on. So in this case, if you had a function of two variables, you would have the input was points in the plane, and the output was the height, f of xy. So you'd have like a, I don't know, like a crazy surface up here. And the region R is the thing that was getting sliced up. Nice region. Anyway, the thing that you put in the bounds of the integral was the base. It's like what the integral is over. This integral is over the region R. And the end result here of this integral is that if that function f of xy was a surface, then the integral gave us the volume under the surface. So what are we going to do next? Well, the new thing we have to do, a different kind of integral, is a line integral, and that's probably the worst possible name. We kind of need to call it like a curve integral. But what we'll do is instead of having the base be an interval or a region in the plane, instead the base will be a curve, maybe in the plane or in space. So the base here was an interval. Here was a region. Now it's going to be, look in the xy plane and maybe like have some curvy thing that's in the xy plane. This will be called C. And then you'll have a function that tells you how tall everything is above each point of C. So you might get like, I don't know, like build a roller coaster over C. The function tells you like how high you are at each point of C. And what you'll end up calculating is like the area of this weird surface where you're going to like chop up C into little tiny pieces and multiply the arc length of the little piece of C, that's ds, times the height to get the areas of these rectangles. So a line integral, it's the same, all the integrals are basically the same thing, where you're adding up all the little bits of something, but it's about what it's over. And this integral, a line integral, is going to be over the curve C. Yep. Is there more on this page? Oh dear. Do I want to talk about this? Okay, so yeah, this is fine. So the way that we will actually end up doing this is, like, when we were splitting up a region into little bits, we decided it would be nice to split it up as like dx dy, or we could split it up as dy dx, and later we split it up as r dr d theta. And in space, we had even more options. But for a curve C, there's only really one reasonable way to do that, which is to make a curve. Back in chapter 14, we wrote the curve as a function r of t. A vector-valued function, it was called in chapter 14. And when you write a curve as a vector-valued function, what you've done is you've parameterized the curve. And I have no idea if there's an e here. We spent a bunch of effort in chapter 14 making sure that you were okay with the fact that there were multiple parameterizations of a curve. And the parameterization is kind of like the directions on how to walk along the curve. It's like you could walk along the curve really fast, or you could go really fast at the beginning and then stop for a minute and slow down and go really slow, or you could go like the other direction entirely. There's lots of different ways to walk along C, and each one is a parameterization of C, and those parameterizations are these vector-valued functions. So what you do is you take your curve, you don't want it to be too crazy, you want it to be smooth, at least like there's multiple pieces that are smooth, so it only has like a couple corners maybe, and you write it as a vector-valued function. Then you slice up the curve by arc length. So you say like, well, okay, go like a tiny bit of the arc length, ds, and then another tiny bit of the arc length, and another tiny bit of the arc length. We don't want to chop up the curve like in terms of x and y. That wouldn't make sense. Like chopping up this curve into little bits, it wouldn't make sense to use like a grid like this. So instead you chop it up according to arc length. Luckily we had a formula for ds already. ds, we had several formulas actually, but ds was x prime squared plus y prime squared, all square rooted, times dt. And that's what we'll use to actually do the integral. Because like to actually do the integral, we need it all to end up in terms of some variable we can actually integrate. So what you'll notice is that line integrals will often have some weird thing here, some weird differential. And to actually do the integral, you have to turn that differential into something you can handle. Let's see if we can actually get into it. Actually do one. Not yet. Pretty soon. Okay, so let's just write down what the line integral actually is. So what I mean by the integral over the curve C of a function, ds, is, well, I have to like turn ds into the right form so I can actually do the integral. And how I do that is I parameterize the function. That gives me t bounds. So I'll get t bounds and it'll be a t integral. And then I just use that formula I had for ds, which was that ds is square root of x prime squared plus y prime squared dt. Then my function, which was f of xy, well, I take this x and this y and put them into the function. This looks really complicated. When you actually do it, it's not complicated. But the main point is, like, your function initially won't have t in it. And you'll need to get the t's in there so you can actually do the integral. And the way you get the t's in there is by parameterizing the curve. So if c is given by this function, that's C is parametrized. It's going to drive me crazy. But I don't know how to spell parametrize. Is there an E there? I don't know. I guess it's not important. Okay, similarly, if instead the curve is in 3 dimensions, that's no problem. You can still integrate a function over that curve, and it's called a line integral, because I've picked a curve that is the base of my integral. And in that case, you'd have the exact same plan. You parameterize the curve, you use the formula for ds that goes with the parameterization. X prime squared plus y prime squared plus z prime squared dt. So all this is ds. And then the function, well, you just have to get these forms of x, y, and z into the function. This makes it look really, really complicated. Let's do one. So here's a function. F of xy is xy. What kind of object is that? Let's turn these things all off. What kind of object is that? That takes inputs of a point, and the output is a number. Then I've got a curve, or a path, C, which is this line segment. And what I want to do is integrate xy, this function, but instead of integrating it over a region or integrating it over an interval, I integrate it over this curve. So how do I do that? How you do that is you parameterize the curve. That's basically the plan for all of this. It's like, if you can parameterize C, then you'll be able to get all of the things in your integral in terms of time, which lets you actually do the problem. So parameterize the curve. To parameterize a line segment, the easiest way to go is to pick a starting point. And then figure out which direction it's headed. The direction it's headed is over by 1 and up by 5. I don't know if you can see these numbers, but this is 1 and 5. The direction is a vector. Over 1, up 5. And then the parameterization is in the x slot, the starting point plus how fast you're moving to the right times t. And the starting point in the y direction plus how fast you're moving in the y direction times t. So r of t, this is my parameterization, is t 5t. A parameterization also comes with a starting time and an ending time. That's important because otherwise this line segment will just be like, wee, and then it goes forever and it's a line. You need a stopping, like a starting and stopping point for t. And if you follow this plan, the reason I really like this plan for parameterizing line segments is that the bounds are from 0 to 1. T equals 0 is the start point. T equals 1 is the end point. We just go from 0 to 1. My parameterization walked this way along the line segment. So this is my parameterization. Why is that good? Well, I want to find the integral of xy ds over this curve C. And the trick is, now that I have a parameterization, I can just use it everywhere. My integral will now be a t integral, with t going from 0 to 1. ds is square root of x prime of t squared plus y prime of t squared dt. So I've changed ds into the form that's useful, that has dt in it. And then xy, I'm going to have to figure out how to deal with that. So I got the t bounds in here, and I got dt here. Now I go, wait, what's x, and what's y, and what's x prime, and what's y prime? What are these things? And the answer is the parameterization tells you. Here's x, and here's y. That's why I was drawing these arrows here, is like, you take your parameterization, and you plug it into the function, so that everything is in terms of t. So x equals t, that was your parameterization. Y equals 5t, that was your parameterization. X prime of t is the derivative of t, that's 1. Y prime of t, that's 5. cool. This is just a number, the square root of 26. And then this is 5t squared. So this line integral, it's not hard. The hard part is parametrizing the curve. If you parameterize the curve, and then you can like keep track of what's going on, that like this is y, so you plug it in for y, then the line integral is really not, it's just not a big problem. So integral of t squared is t cubed over 3. And we're going from t equals 0 to t equals 1. Plug in 1, and you get that this line integral comes out to 5/3 the square root of 26. Which, whatever that is. So that's a line integral over a curve. All the challenge of the line integral over the curve is to parameterize the curve and then plug in what everything equals. This ds is the ds we used earlier. So you really need that this is ds. Hopefully we get to say why you would ever do that. And the reason you would do that is for mass. Yes, great. Okay, so who cares? Why would you ever do a line integral over a curve using a function? The reason is, what if the curve has a different density at every point? That density is a function of x and y. So if you have a density function, and you've got some wire, and the wire is like this, we're not looking at the region. It's not like we're filling in this region. No, we're just talking about this wire. And we say, well, the wire has a different density in each place. What's the mass of the wire? Okay, well, the mass of the wire would be, take a little bit of the wire, this will be its length, ds, and multiply by its density, and that'll give you mass. So here's dm, a little bit of mass, is the density times a little bit of length. If you integrate that, you get the mass. So, when this question asks you find the mass, you say, no problem. The mass of the wire, which is in a curved shape, is the integral of the density times a little bit of length. Okay. I'm going to need to parameterize the curve to get the c out of here, but I can get the density function plugged in. The density equals x, according to this question. To get the c out of the integral, I need a parameterization of this curve. So let's do it. Because the curve kind of has two pieces, I think we'll have to, we'll have to figure out a parameterization in two pieces. Also, what is this curved shape? What is it supposed to be? Is it supposed to be a parabola, I guess? Kind of need more information. Oh, on my original version of the notes, it told me that this is the line y equals 2x, and this is the parabola y equals 2x squared. Does that make sense? Yeah, if x is 1, y is 2 in both cases. Okay, cool. So what you do, you need to parameterize this stuff. So I'll say, okay, I'll call this C1, and I'll call this C2. Let's get a parameterization of each. And then we'll split up this integral into the two pieces. So C1, the curve is not going to equal its parameterization. The curve has a parameterization. C1 is just a line segment, so I'll use the same trick as before. I have a starting point, which is 0, 0, and then it's going over 1, up 2. So I'll go over 1 for each time, and up 2 for each time. Using that plan, my bounds are just from 0 to 1. So this is my parameterization of the line segment part. For C2, when I have a function, like y equals some function of x, the easiest parameterization is to let x equal t. If x equals t, then you can plug t in for x and it tells you what y equals. Then you use for your t bounds, you use the x bounds because you're letting x equal t. In this case, t also came out to being from 0 to 1. But this is just, for a line segment, I have a fast way to parameterize a line segment. For a piece of a function, this is like a function of x, this is my fast way to parameterize the function of x. In both cases, I can like drop this parameterization into the line integral and I'll be able to get what I want. So here's the mass of the first part. I have an integral over c1. To get c1 out of here, I turn it all into the parameterization. So c1 had t going from 0 to 1. X equals t from the parameterization. And ds is square root of x prime squared plus y prime squared dt. This is just what ds equals. Let's leave x here for now because it's kind of confusing otherwise. In the parameterization for c1, x equaled t. X prime was 1 and y prime was 2. So I just have a factor of square root of 5, and then I can integrate x. Wait, x? Oh, x equals t for c1. Notice that all the work is in getting the parameterization to line up and make sense. So integral of t dt is half t squared. I have this weird square root of 5 floating here. And I'm going from t equals 0 to t equals 1. So I get half square root of 5 for the c1 component of the integral. Then I'll do the c2 component. Same deal, I'm going to change the bounds into t bounds from my parameterization. Then I'm just going to leave x alone for now, and I'll just translate ds into what ds equals. Because I'm dealing with a function of x and y, I just have x prime and y prime both squared. Then, for this parameterization, what is x? Well, x is t. What's x prime of t? X prime is 1. And what's y prime of t? Oh, y prime of t is 4t. So this integral will be a little bit more complicated because I have t square root of 1 plus 16t squared dt. But it's nothing too crazy, it's just a u substitution. Let u equal the inside function. du is 32t dt. I have t dt, so I'll divide both sides by 32. And then I'll change the bounds because I'm in calculus 3. My t bounds were from 0 to 1. My u bounds will go from, well, plug in 0 for t, I get u equals 1. Plug in 1 for t, I get u equals 17. So I have the integral of a 32nd du square root of u from 1 to 17. Okay. The integral of u to the 1/2 is 2/3 u to the 3/2. So I'll have a 48th u to the 3/2 from 1 to 17. Great. I'm super out of space. So this is a 48th of 17 root 17 minus 1. So this is the mass of the C2 part of the second part of the wire, and this is the mass of the first part of the wire. The overall mass is this mass plus this mass. And these don't, nothing good simplifies here, so you just add them together. So that's a line integral over a curve that you need to parameterize in 2 pieces. Just like you're allowed to split up an integral over an interval into 2 subintervals, you can also split up the curve into 2 subcurves and just parameterize them separately. And you just do them separately and add them up at the end. Okay, I think that's it for integrating functions. Now we're going to try to get into the second half of the section, which is how to integrate vector fields. So, why? Why would we do that? Well, we would do that because our favorite vector fields are force fields. And if you multiply a force times a distance, you get work. So you can ask questions like, say the wind is blowing and swirling all over the place. Say that I drive somewhere. does the wind help me or hurt me? Let's take a look at our wind map here. This was my Hurricane Sandy wind map. Say that the wind looked like this on the day that you were driving cross country, and you drove from Denver to Columbus. The question is, would the wind generally help you on your journey, or would it hurt you? What's the work that the wind does on you if you were driving directly from Denver to Columbus? Well, at first you'd say, okay, well, during this part of my journey, the wind is helping me. And then during this part of the journey, the wind is hurting me. And then during this part, the wind is helping me a lot. So in total, by adding up all the contributions of all the wind on this path from Denver to Columbus, the wind helped me in total. And that totaling of the force along the curve, that's a line integral of a vector field. We'll do a lot of examples. Okay, so if we want to follow that plan where we're trying to add up all the little contributions of the wind, which is a vector field, along a path that we're driving, how could we possibly do that? So this is what we would do. We'd say, get your curve C, which is now a curve in space. So it's not just a curve, it's not just a path on the surface of the Earth necessarily. You might say, oh, well, I'm going to fly up and go in a circle and then go to Columbus. Because we've got a curve in space, now we're looking at the input is time and the output is a point in space. This is your curve. So the curve will be parameterized by a vector valued function that has the input of a number and the output is a location in space. So this is going to be our curve. Then, separate from that, there's going to be a vector field, which is where the wind is blowing at each point. That takes as input a point, and its output is a vector. So at this point, maybe the wind is blowing this way, and at this point the wind is this way, and at this point the wind is this way. And there's all these vectors all over the place. Technically there's vectors over here too, but whatever. This is the vector field. And I'm not sure what notation I want to use for the vector field. It's just going to be dicey. So this is a vector in 3 dimensions. So this picture has our 2 most complicated objects, both on the picture at the same time. It's a path through space, which is a function that takes numbers as input and output is a point in space, and a vector field, which takes input of points in space and outputs vectors in space. And the question is, what's the total contribution of the vector field? I lost my mouse. Can I have it back? Great. What's the total contribution of the vector field when I walk along this path? So the integral of, over this curve, that's why it's a line integral, is because it's all based on this curve. How do I tell if the force is helping or hurting along this path? And what you do is, let me ask, and maybe you can figure it out. Say you're up at this part of the curve, and you're you're driving east or you're flying east, and the wind is blowing this way. Is that helping you or hurting you? Is the wind at your back, blowing you along your curve to help you? Or is the wind in your face, slowing you down? The answer is that at this point in your trip, the vector field is doing neither. It's orthogonal to your path. So in this kind of situation, we want the contribution of the vector field to be 0. In this area, we would say, well, I mean, it's not entirely in your face, but it's partially in your face. So we want to say that the vector field is working against you here. And over here, where the vector field is normal to your curve, we say that the vector field is not contributing either way. How do we get a vector and another vector to give us 0 when they're orthogonal? That's the dot product. So what we do is we take the integral of the vector dotted with dr, a little bit of direction of which way you're headed on the curve. In this area, you'll have f dot dr equals 0 because the direction your curve is headed and the direction of the vector field are orthogonal. So you'll get 0 for that part. Where over here, because they're like opposed to each other a little bit, you'll get a negative number. This integral is the line integral of a vector field. I guess technically f is also a vector, which is good because we're dotting them together. So this is the line integral of a vector field. If you add this all up, then what you get is the work done by the vector field as you walk along the curve. I'm imagining that this is probably outlining what I just said. Yeah. There are a lot of ways to say this. I think I've said this before, but anytime you don't like my explanation, you have the internet. Just go find another explanation. You also should have access to the textbook, I guess. That should also have another separate explanation. Anyway, how will we actually calculate the line integral? Well, you shouldn't be too surprised to find that the way out of the integral over a curve is to parameterize it. If you parameterize the curve, as a vector valued function, then you can say, okay, well, dr, I don't know why we have this middle segment in here, but dr is r prime dt. And we know how to find the derivative of a vector valued function from chapter 14. You take the derivative in each component. So this dr part of the line integral is not a crazy, like, ridiculous object. It's just dr dt times dt. So you take the derivative with respect to time and multiply by dt. It's possible that this form is useful in physics or something. I don't know why it's here, but I've always just skipped directly to this part. So then when you are trying to find the integral of f dot dr, you know what dr is. Dr is r prime of t dt. Then you can get the t bounds on your integral. And then your vector field, it had inputs of x, y, z. Well, you, just like we did in the early part of the section, you drop your x, y, and z from the parameterization into your vector field function. X, y, z in here. So that's these. That'll be the line integral of a vector field. Let's do some. So we're going to take a path that's r of t is cosine t, sine t, t, which is like the basic three-dimensional path that we have played with. It's a helix. At t equals 0, you're at the point 1, 0, 0. And then you kind of like spin around and come back. At the point, when t equals 2 pi, you get 1, 0, 2 pi. When t equals 0, you're at 1, 0, 0. So it's just one curl around a helix. Then you say, okay, you're going to take this path, but the wind is blowing, And I'm stuck on the wind, but it doesn't have to be the wind. It can be any source of force. So it could be a gravitational field, or if you've taken more physics, there's plenty of like force fields that you could have floating around in space. We'll just use this force field. How do you find the total work done? Well, the work is add up all the little force times distances. And to get C out of here, you use the parameterization. Well, here's my parameterization. The t bounds are from 0 to 2 pi. F is f of xyz, which is minus x minus y minus z. And it's going to be dotted with dr, which is the derivative of this thing, dt. I don't know, like x prime, y prime, z prime, dt. Now, what are all these x, y's, and z's doing in here when we're trying to get a t integral? That's what the parameterization is for. X equals cosine t. So x is cosine t, y is sine t, z is t, and then this is an actual literal dot product in here. X prime, well, x is cosine t, so x prime is minus sine t. Y is sine t, so y prime is cosine t. Z is t, so z prime is 1. Now I have everything all in terms of t, but I've got like a product in here. How do I deal with the dot product inside an integral? The answer is just do the dot product. So I multiply each component and add up the results. So I'll have sine t times cosine t. In the y component, I have minus sine t cosine t. In the z component, I have minus t times 1. Add all these together, and then I'm going to integrate it dt. These just cancel? Awesome. So I have the integral from 0 to 2 pi of minus t dt, which can't ask for a better integral than that. Plug in 2 pi and I'll get 4 pi squared. So I have minus 2 pi squared. So here's the permanent question. It's like, what's the deal with the sign of this value? Like when I get a positive number versus when I get a negative number. If you dot two vectors that are going the same direction, you get a positive number. If you dot two vectors that are going in opposite direction, you get a negative number. So this outcome means that if you add up all the contributions, in total, it's like the force was pointing opposed to the direction vector. So in total, the force is like going against us as we walk along this path. Again, the reason for that is just that when you dot two vectors that are opposing each other, you get a negative number. So this means that the force is like working against us. So the force, I guess we just say that it did minus, I don't have units, so it's hard to finish the sentence. Minus 2 pi squared work on our particle, on our object. If the force helped us along, we would say that the force did the work for us, but instead the force worked against us, so we ended up with a negative number. Maybe if you've taken a lot more physics than me, that part of the problem is easier. For me, I haven't taken as much physics, so for me, I have to go back to why do I get positive or negative numbers from the definition. This is not necessarily a weakness. This is part of why you take these kinds of subjects from multiple departments to get the different perspectives. For me, I'd always rather go back to the picture, to the definition that says, oh, this is a dot product. Why would the dot product be positive or negative? Okay, let's do one more. So here's I have a curve. And again, I don't have the equation of the curve here, but it looks like in my notes it's y equals 2x squared again, this curve. And we're going up to the point 2, 8. Now I'm not in space anymore, so my curve isn't in space. Instead, I have a curve in the plane, but I still have a vector field that's acting on it. So I've got some arrows all pointing everywhere, and I want to know if the arrows are helping or hurting. Well, integral over c of f dot dr, we should first parameterize the curve. This is a function, so the easiest parameterization will be to just let x equal t, and then y will be 2t squared. Then the t bounds are the same as the x bounds because I let x equal t. So x goes from 0 to 2. So I'll say that t goes from 0 to 2. This is my parameterization, and that's what lets me do the integral. So I'll have t bounds here, 0 to 2. My force vector was x to y. And dr is the derivative of my, dr is r prime of t dt. So the derivative of my parameterization, dt. It wouldn't be smart to do this dot product yet because I'm hoping to get everything in terms of t. And this is the place where students get stuck the most, is where like, what do I do? And the answer is, what is x? Did you actually say that x equals something anywhere? Like, did you say that y equals something anywhere? You're aiming at getting everything in terms of t. And the answer is yes. That's what a parameterization does. It tells you what x and y equal. So x equals t, and y equals 2t squared. So I have 2 times 2t squared. Now it makes sense to do this dot product. So t times 1 plus 4t squared times 4t. You can actually see that the y component of the force is the one that's actually contributing the most to what's going on here. I'll try to get a picture of the vector field here in a second, but let's finish the problem. Integral of t dt is half t squared. Integral of 16t cubed dt is 4t to the fourth. Plug in 2 and we'll be done. So 2 plus 4 times 16. So I get 66 total work done by this vector field when I walk along this curve. This implies that the vector field is actually helping us, that like the vector field is, the wind is at our back. Let's get a picture of it using this field play. So in the x component of the vector field, we've just got x. In the y component, we've got 2y. So here's what the vector field looks like. Here's the origin. And the vector field kind of like explodes outward. In particular, our path was along a parabola like this. And yeah, the vector field is like really helping us. It's at our back when we've parameterized the curve this way. So I'm not surprised to get a big positive number as the answer. I think I said this in the last video, but just in case, if you want that tool, you should Google Anvaka field play. So that's how you do line integrals of a vector field over a curve. That's our fourth objective up there. And you usually do that to find the work done by a force over a curve. And that's the fifth objective. So the last thing we need to do in this section is figure out what the differential form of the line integral is. Okay. So to write down the differential form, what we'll do is we'll say, let's say you have your vector field, f of x, y, and you write it as like this. That your vector field has two functions in it, and you'll call them m and n. Because you've written your vector field as mn, now these are like functions that we can take the derivative of like normally. So let's see how that shows up. When you find the integral over a curve of f dot dr, you parameterize the curve like usual. I'm just in 2 dimensions here. So it's going to be x of t, y of t. And you use that to get going on your vector field calculation. So you're going to have some bounds from a to b. The vector field is m of x of t, y of t, n of x of t, y of t. And you're dotting that with dr. So you're going to have x prime, y prime, dt. This is how we did it before, was we said, okay, your only way out is to get everything in terms of t. The differential form of the line integral says, well, what if you put off getting everything in terms of t until later? So what if instead you said, instead of writing dr as x prime of t dt and y prime of t dt, instead you could just say, what if dr was just dx dy? Then you would have, I can't write bounds yet, I have to write like the curve because I haven't gotten everything in terms of t yet. Then you would have m, and there's no t's yet. Here's f dot dr. And so what you would end up with is m dx plus, because of the dot product, n dy over the curve. You will often run into this form in like, I've seen it in a couple of like PowerPoint slides from engineering classes where this is just like another way to think about the line integral of a vector field over a curve, is to say, let's not parameterize the curve just yet. Let's get the dot product done first. And if you do the dot product first, where you're doing the f dot dr first before the t's show up, you get this. It looks like this. You can still get the t's involved later. The way that you get the t's involved later is you notice that then later you can write dx as x prime of t dt. And dy is y prime of t dt. So the point of me bringing this up is not that it's like another way for you to do the problem. Like, I don't see any particular benefit to you like thinking of this as a totally different way to do things. It's more that if you run into this notation someday with like a dx and a dy, that you should not be worried about it, because you can always turn everything into t later if you need to. Dx is dx dt dt, and dy is dy dt dt. So it's fine. Last page is a couple of other things that we will be able to calculate with line integrals. We won't always calculate work with line integrals. You can also calculate other things. The main things that you can calculate with line integrals other than work are circulation and flux. So let's look at circulation first. If you have a vector field, f, so we're thinking of like wind swirling around in space, and then you have a curve, which is also in 3 dimensions. Switch the arrow over my head here. A curve C that's a closed curve. So we'll say like it goes under the x-axis and like over the y-axis and then like over here and behind the z-axis and like back down. So say you have a closed curve C. Smooth closed oriented curve in D. Okay, D is the region where the vector field makes sense. I don't know why we've named D here. But the vector field is like swirling around, maybe. There's just every point in space has an arrow. Every point in space has a vector. And C is a closed curve. It loops back around. The question you could ask about the interaction between the loop and the vector field is, if you walk all the way around the loop, does the vector field help you or hurt you? That's called the circulation, which I've misspelled. The circulation of the vector field on the curve. It might happen that while the vector field is all swirling all over the place, maybe over in this section, the vector field is like all about helping. And in other places, the vector field is kind of like not helping or hurting. In that case, we would say that the vector field in total has positive circulation on C. How do you find it? Well, this is just the same question of whether the curve and the vector field are pointing in the same direction and how much they're pointing in the same direction. So circulation, you get the exact same integral. It's the integral of f dot dr. If you're trying to test how much do these vectors point the same way, you dot them. Do the integral over the curve C. You get one little piece of decoration on this integral, which is if the curve is a closed curve, it's a loop, you get to make this sweet little loop on the integral, makes your integral look fancy. And that tells you that this curve is not just any curve, it's a closed curve that comes back to where it started. So this is the circulation. This is the definition of circulation, so yeah. Okay, let's do this. I've got some arrows in space. I've got a curve in space. This is a tilted ellipse. So there's an ellipse kind of like however it's oriented, and then there's vectors pointing everywhere. And the question is like, are the vectors helping or hurting? The answer is just do this line integral. F dot dr. We have the parametrization set up, so we can use it. T goes from 0 to 2 pi. I'm going to get everything in terms of t. dr is all these derivatives dt. So here's dr. I have not left nearly enough space. dr is the derivative of r dt. So that's all this, dr. F is this vector field, z, x, y, and they're dotted together, f dot dr. The problem is, I don't want to deal with this. I wanted it all in terms of t, but it's not really a problem, because I know what x, y, and z equal. It's in the parametrization. Z is cosine t, x is cosine t, y is sine t. Then I can dot these vectors together. I'll get an actual scalar to integrate. Cosine times minus sine. The y component contributes cosine squared. The z component contributes minus sine squared. I have to say I was hoping for better. I was hoping for some cancellation here. In fact, I'm hoping for cancellation so much that I'm going to go back and check my work here. Just because I highly doubt that this is actually the question. Yep, I missed a minus sign. So it's supposed to be minus y, minus sine t. That turns this into plus sine t. We didn't exactly get cancellation, but we kind of did. Sine squared t plus cosine squared t is 1. I'll use one more trig identity, which is that sine 2t is 2 sine t cosine t. So sine t cosine t is half sine 2t. Then I can do these integrals. The integral of half sine 2t dt is minus a fourth cosine 2t. The integral of 1 dt is t, from 0 to 2 pi. When I plug in 2 pi or 0, I'm going to get the same thing for cosine 2t, so these cancel. And the final answer is 2 pi. What this means is that the x component of the vectors, its contributions all canceled out. But the y components and the z components of the vectors gave me enough of a push that it all added up to a positive contribution towards like the direction of the curve. So it had a positive circulation. We'll deal with circulation more later. But anyway, the other thing we can do is we can find the flux of a vector field through a boundary. This would be kind of like if you had a doorway, like an opening, an open door, and you wanted to say, well, sure, there's wind everywhere. Is the wind like blowing air through my door? Or is it kind of like just going parallel to the door? Is there any flux of the air through the door? Now we're not asking, like, let me get the picture here, where we'll have like a boundary C. And there's some vectors everywhere. Let's say some of the vectors are like sending stuff inside, and some of the vectors are sending stuff outside. In total, is there like air leaving the inside of C, or is there flux coming into the inside of C? That's the flux. Instead of asking whether the vectors are going the same way as C, like the circulation, now we're asking whether the vectors are pointing in or out of C. So now instead of asking whether they agree with the direction of C, now we're going to ask whether they agree with the normal vectors to C. So instead of f.dr, we're going to add up. We want to know if the vector field is pointing the same way as the normal vector. So we'll do f.n ds. I don't think we have any examples to do here. It's just, there's lots of different line integrals. The first kind we did was the line integral of a function, which we used to find mass. The second kind of line integral was the line integral of a vector field, which turns out to be much more important because it's used to find work done by a force field. We can also use it to find circulation and flux of a vector field when we have a closed path. Do some practice problems. You'll find that once you know what you're doing, there's like nothing to do. Like you're just like, oh, it says X. I'll plug in X. But keeping your brain wrapped around all the different concepts is the hard part. So hopefully this is a cool payoff section. We'll get to do some really neat stuff with line integrals later in the chapter. Go do some homework.